Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 8, Lesson 11 on solving linear quadratic systems. So we had a unit entirely devoted to solving linear systems of equations. That was like Unit 5 or I don't know, it seems like it was forever ago, all right? So we've solved systems of equations before, but we've never solved a linear quadratic system. So let's talk a little bit about what in the world these things are. Linear quadratic systems of equations. A system that is made up of one linear equation and one quadratic function are known as linear quadratic systems. They can be solved either graphically or algebraically, and you're expected to know how to do both of them. So just remember, like a system of equations is just two or more equations. And way back when we were solving systems by substitution or elimination or whatever, both of the two equations that we had were linear, meaning that the highest power in both of them was x to the first, y to the first. Now what we're going to do is we're going to throw in one quadratic function, one linear function, and we're going to solve it. So let's bring them up. Exercise number 1. Consider the system of equations shown below, y equals x squared minus 8x plus 15, and y equals x plus 1. Letter A. Solve this system of equations graphically on the grid provided. Label the equations. All right, so let's remember how to solve a system of equations graphically, right? When we solved a system of two lines graphically, we graphed both lines and we found their one and only intersection point. When we graph a system of two equations, one of them being a parabola, right? We're going to graph it and we're going to find their intersection point or points, because it could be one intersection point or possibly two or I don't know, whatever, right? But let's take a look. Now, big difference between these and the ones we did back when we had linear systems. When we had linear systems and they were both lines, we could graph both of the lines using like kind of slope and y-intercept. This time I've got a parabola, which I'm going to want to generate a table of values for and a line. Let's first graph the line together and review that, right? So if I want to graph this line, right? This is a line, right? Then, that looked a little funny, right? Then I've got a slope equal to 1 over 1, and I've got a y-intercept of 1, right? So graphing this line should be pretty easy. I'm going to go up, I'm going to plot my y-intercept of 1, and then I'm going to go to the right one and over 1, right 1 over 1. I'm going to give that kind of classic line that goes through all of those diagonal points, okay? And I'm going to just kind of freehand sketch it at this point. Okay, and as always, whenever you graph a system of equations, be sure to label the equations. Now, there's absolutely no reason why you couldn't also generate a table of values for that line. Okay, feel free. If you don't feel comfortable using the slope and the y-intercept of a line to graph it, then certainly put this into your calculator, ask it to generate a table of values, and use that. Let's now put, though, the parabola into our graphing calculator, generate a table of values, x, y values, and graph that. All right, so I'm going to bail out of here. All right, open up my TI Inspire, and I'm going to put in a graph. All right, so I just want to put that parabola in. It's x squared minus 8x plus 15. That just got way, way smaller. I'm going to go back to handheld, and it continues to be small, so we'll drag it out, get a little bit larger, and go back here, still small. Lovely, drag it out, make it larger. Wow, gonna be one of those days. All right, let's see if I can do this. 8x plus 15. 8x plus 15. Enter. There's my nice parabola. It doesn't do me much good in that sense. I'm going to go into a table. So I want that table of values. Now I have to just find the values that are going to fit. And hopefully not scroll to infinity and beyond. Let's see. 0, 15 won't fit, but 1 and 8. 1, 8 will fit. 2, 3, 3, 0, right? And again, I'm going to have to put this on the smaller view in just a moment, but my point before I put it on the smaller view, and you can't see it very well, is that these are the tables that I'm going to go with, right? I'm going to have like x equals 1, y equals 8, x equals 2, y equals 3, etc. I actually can even fit the 0, 15 in there, so I think I'll put that one in as well. Unfortunately, I have to make this calculator smaller in order to even get my table down. So make sure that you've got this kind of all down and understand what's going on, and you have your own table of values sitting there, because I'm going small now. All right, handheld only, always in front, view full screen. Here we go. I'm just going to put this over here for a moment so I can get my table of values. All right. Got x, y. What do I have? I've got 0, 15, 1, 8, 2, 3, 3, 0. Let's bring some more up. 4, negative 1, 5, 0, 6, 3, 7, 8, and maybe one more, 8 and 15. All right, now I can graph my parabola. All right, I've got 0, 15, way up here, 1, 8, right here, 2, 3, right here, 4, negative 1, oh, sorry, wait, 3, 0, sorry, missed that one. 4, negative 1, 5, 0, 6, 3, 7, 8, that sounds funny, and 8, 15. So I'm going to draw my parabola in now. Nice and smooth. All right, I'm going to label it with its equation, which I have to do way up here. Y equals x squared minus 8x plus 15. All right, so I've got my graph. All right, now I've got to actually write down my solutions. Now the solution to a system of equations is always where the two graphs intersect, okay? So they intersect here, and that's at the point 2, 3. I apologize, that's going to get lost a little bit. And they intersect right here, which is at the point 7, 8. And that's it, right? There is my system of equations. Now I'm going to bring out my calculator just for a moment, because I would be a little bit remiss, right? A little bit negligent if I didn't say to you, look, you can find these two values using the intersect command on your calculator, okay? But the key is you do have to be able to produce a graph, right, on a grid, which is why you need to know how to use that table. But just for a moment, right, since I've already got my parabola in there, I'm going to get rid of my table for a second. Don't worry, I'll make it big in a moment. I'm going to remove my table, okay? In fact, let me bail out of here just for a minute, all right, so that I can go on the bigger screen. And I am going to double click into here, which should allow me to put in an fx2. So I'm going to put in my linear equation, x plus 1. All right, I'm going to make my window just a bit taller. All right, all I need to have is my y max a little bit bigger. I'm going to maybe make that 15, bring it up there. All right, and what I see is I've got my two graphs, right? I've got my linear graph and I've got my quadratic graph. And one of the great things about your graphing calculator is if I go into my menu and I go into Analyze My Graph, one of the main things here, and we've used this before to solve equations graphically, is my intersect command, right? My intersect command basically asks for a lower bound, so if I drag that vertical line to the left of this intersection point, which is pretty hard to see right now because the color is pretty dampened, if I hit enter, and then I drag it to the right and hit enter, I get one of the two intersection points. If I do it again, menu, analyze, intersect, but now I kind of bring it here, enter, drag it past that intersection point, hopefully, enter, then I get my other intersection point, right? So I can certainly use my calculator to solve a system of equations graphically, right? It does a beautiful job finding the intersection point at 2, 3, and 7, 8, which is exactly what I got when I did it by hand, 2, 3, and 7, 8. But again, I can't emphasize this enough. Very often you will have to solve these by creating a table of values and graphing. All right, so make sure that you can do that. Let's go back into full screen, and now let's take a look at letter B. Solve the system algebraically by using the substitution property of equality. Show the work that leads to your final answer. All right, so when we solved linear systems, we saw how to solve them graphically, which we just kind of reviewed there. We saw how to solve them with substitution, and we also saw how to solve them with elimination. We're not going to be solving anything with elimination in linear quadratic systems. We're going to solve by substitution. And remember, substitution is very easy, right? When two things are equal, as they are right here, I can then take x squared minus 8x plus 15, and I can substitute it in for that y. Or I could take x plus 1 and substitute it in for that y. I'm going to take this and I'm going to substitute it in there and start by doing what many teachers say is setting the two equations equal to each other. Right? And by setting the two equations equal to each other, what I'm really asking is, for what x values will the y values be the same? That is literally asking, where do I have intersection points? Now, how do I solve this algebraically? Well, since the equation's got an x squared in it, I have to use one of my techniques that I've used to solve quadratic equations. Now we have two techniques, right? We have solving by using completing the square, and we also have solving by factoring, okay? Now, which one I use, I still kind of want to get everything on one side of the equation. So let's do this. Let's subtract an x and a 1 from both sides of this equation. That's going to give me x squared minus 9x plus 14 is equal to 0. Now, how do I want to solve that? Do I want to solve it by factoring? Do I want to solve it by completing the square? Well, for me, I would much rather solve this by factoring because the linear coefficient is odd, right? If that was an 8, a 4, a 6, something like that, I might actually consider using completing the square to solve this. But because it's a 9, there's no way I'm going to do that. Anyway, we just spent quite a few lessons solving equations based on the zero product law, so I'd like you to go ahead and solve this using the zero product law. Pause the video now and go ahead. All right, well, it's pretty easy, right? I'm looking for two numbers that have a product of 14 and a sum of -9. They've got to both be negative to have a positive product and a negative sum. I think I've said that quite a few times. Those two numbers happen to be -2 and -7. So this is going to factor as x minus 2 times x minus 7. That almost looks like an x equals 0. That means I can take, nope, we need to go back down. I can take, how many times can I say I'm going to take x minus 2 and set it equal to 0, x minus 7 and set it equal to 0, add 2, and I'll get x equals 2, add 7, and I'll get x equals 7. Now, you are never done solving a system of equations when you have the x values, unless literally they just say, give the x values that solve the system, I don't care about the y values, right? But once we have our x values, we have to come up with our y values. Now, how do I do that? Well, these two functions literally convert x values to y values. So you can take these two x values and you can put them in either into this equation or into this equation to figure out what the y value should be for each one of them. Whichever one seems easier to you, use the second one. Whichever one seems easier to you, that's the one you should do. Again, this one's the much easier one to use, unless you really want to square it, multiply it by -8 and add 15. I'm just going to add 1 to each one of them. So y is equal to 2 plus 1, so y is equal to 3, giving me the coordinate point 2, 3. Y is equal to 7 plus 1, y is equal to 8, giving me 7, 8. All right, and that is exactly what we had up here, right? When we solved it graphically, we found they intersected at 2, 3, and 7, 8. And when we solved it algebraically, we found that they intersected at 2, 3, and 7, 8. Easy, right? And every one of these that I solve algebraically, I'm going to solve by substitution, all right? Maybe I'll use the zero product law, maybe I'll use completing the square, but regardless, I will always have a quadratic equation that I have to solve. Always, always, always. So let's play around a little bit more, all right? Now, Finding the intersection points of a line and a parabola can be challenging graphically. It's often easier to actually just find them with algebra, okay? So let's take a look at a situation where we don't solve graphically, we only solve algebraically. Exercise number 2. Algebraically determine the 2 points of intersection of the functions shown below. F of x equals 5x plus 3, and g of x equals x squared minus 3x minus 17. Now, please don't be bothered by the fact that it says f of x and g of x. These are still y equals 5x plus 3 and y equals x squared minus 3x minus 17. So I'd like you to solve this problem exactly the way that we solved part B in the last problem. Pause the video now and see if you can figure out algebraically where this parabola and that line intersect each other. All right, here we go. I'm going to set the equations equal. So I'm going to get x squared minus 3x minus 7 is equal to 5x plus 3. Okay, great. Step 1. Step 2, get the entire equation equal to 0. To do that, I need to subtract a 5x from both sides, and I need to subtract a 3 from both sides. When I do that, I'll get x squared minus 8x minus 10 is equal to 0. Now here the linear coefficient is even, right? So I could totally use completing the square. But for me personally, I only use completing the square to solve a quadratic when I look at that quadratic and I go, man, I just don't know how that factors, right? So if I have to kind of work really hard to factor it, then I will not tend to actually use the zero product law, all right? But in this case, oh shoot, in this case, I can. I'm looking at that thinking, going, I don't know how it factors, and that's because this is a 17, but I only put down a 7. So making that into a 20 makes it much, much easier to factor. I'm like, two numbers with a product of negative 10 and the sum of negative 8. I can't think of what those two are. This is now going to be a lot easier, right? So I need to now factor that trinomial, okay? Sorry about that. Oh my. Those two numbers are going to be negative 10 and positive 2. So I'll have x minus 10 is equal to 0. X plus 2 is equal to 0. This will give me a solution of x equals 10. This will give me a solution of x equals negative 2. Now again, just like I mentioned before, right? Those are the x values of intersection, but I also need the y values. You can substitute them into the function f of x. You can substitute them into the function g of x. It does not make a difference. I still think the function f of x is easier, right? I have to take x, multiply by 5, and add 3. So I think that's still going to be the simpler one. So I'm going to use this thing to figure out my y values. Y is equal to 5 times 10 plus 3. That's going to be y equals 53. And in this case, it's going to be y equals 5 times negative 2 plus 3. That's negative 10 plus 3, and that's y equals negative 7. And so at the end of the day, my two intersection points are 10, 53 and negative 2, negative 7. And of course, you can kind of see, especially with that first intersection point at 10, 53, that especially by hand, if you were doing a graph by hand, not using your calculator, but by hand, this one would be a tough one to find simply because of how large that y value is. Now, using technology, it wouldn't be that bad, right? We would have our calculator graph the linear and the quadratic function, make our y window large enough, and we'd see that intersection point, and using the intersect command would find it easily enough. But if I had to do it on a piece of graph paper, this thing would be a pain. This one I could find pretty easily. And yet the algebra of finding them isn't that hard, right? Set the two functions equal to each other, right? Set the two functions equal to each other. That's really just substituting one y in for the other y. Get everything equal to 0. Factor, hopefully write down the right function right there. Factor, use the factoring to find the x values of intersection, 10 and negative 2, and then use one of the two functions to figure out the y values, whichever one's easier for you. All right. Now, that's really the way that you solve a linear quadratic system every single time, okay? Now, when solving these types of systems, we have to be prepared to use the zero product law and all types of factoring. So let's take a look at a multiple choice problem in this situation. Exercise number 3. Which of the following sets represents the x-coordinates of the points of intersection of the line and the parabola shown below? Excellent. So in this case, I am not looking for the full coordinate point. I just want the x-coordinates of the points of intersection. So each one of these choices, these aren't coordinate points, right? If they were, there'd be parentheses around them, not the squiggly set brackets. These are the x-coordinates. So I'd like you to see if you can do this. Set the two functions equal to each other, right? And then use the zero product law or whatever you want. I mean, here we're talking about the zero product law to find the two x values. Now, of course, one option on this would be to slap both of these into your graphing calculator, graph, use the intersect command to find those x values. But let's take a look at it algebraically. Here we go. I'm going to take x squared minus 12x plus 7, and I'm going to set it equal to negative 8x plus 7. Assuming I'm using the zero product law on this, I've got to get everything equal to 0. That's going to require me to add an 8x to both sides and subtract a 7. All right, so I'm going to add an 8x and subtract a 7. All right, nothing combines with that x squared term. It just kind of comes on down. Negative 12x plus 8x is negative 4x. Positive 7 minus 7, that's 0. So my constants have all gone away, and I get x squared minus 4x equals 0. Now, this is one of the most dangerous equations for students I've noticed over the years, because they see that x squared, they see that minus 4, and they think difference of perfect squares, x minus 2, x plus 2. But this is not the difference of perfect squares because there's an x to the first sitting right here. If that had just been x squared minus 4, then x minus 2 times x plus 2 would be perfect. But this is, strangely enough, GCF factoring, right? Because there's an x squared here and an x to the first here. I can rewrite that left-hand expression as x times x minus 4 equals 0. It does not factor as x minus 2 times x plus 2. It doesn't, right? That's the way it factors. But once I have it factored that way, I can take this factor and set it equal to 0. And I can take this factor and set it equal to 0. Strangely enough, in the first case, I don't even need to solve anything. It's already solved. X is equal to 0. The other one gives me x equals 4, which means the correct choice is 0, 4. I cannot tell you how many times over the span of my career I have seen this equation or x squared minus 9x or x squared minus 16x, something where that number, that coefficient multiplying x is a perfect square, and people immediately say, oh, difference of perfect squares. But the difference of perfect squares always has to be the variable squared minus just simply a number squared. It can't be a number times x to the first. That is no longer difference of perfect squares. All right, let's take a look in the next exercise at kind of an interesting and unique exercise or example. Our last look at linear quadratic systems involves a very special case. Exercise number 4. Consider the linear quadratic system shown below. Solve this system algebraically. Show how you arrived at your answer. Okay, great. So we've done this quite a bit already in this lesson. I'd like you to set the two equations equal, right? Solve for x, get your x values, plug them into maybe the first equation probably, get your y values, and go from there. All right, so pause the video now and solve this system algebraically. All right, let's do it. So first things first, I'm going to set those equations equal to each other. I'm going to have x squared minus 4x plus 5 is equal to 2x minus 4. All right, to use the zero product law, I've got to get everything equal to 0, so I need to subtract a 2x and add a 4 to both sides. All right, I'm going to get x squared minus 6x plus 9 is equal to 0. Now, before I move on here, right, I need to factor this. I need to find two numbers whose product is positive 9 and whose sum is negative 6, which means both numbers have to be negative. And in fact, the two numbers are negative 3 and negative 3, right? Negative 3 times negative 3 is positive 9, and negative 3 plus negative 3 is negative 6. So this is a little bit of a strange situation because I get x minus 3 times x minus 3 is equal to 0. which means x minus 3 is equal to 0, or x minus 3 is equal to 0. So x is equal to 3, or x is equal to 3. Now, if x is equal to 3 or x is equal to 3, I just want to mention that x is equal to 3. All right? There is only one solution to this particular equation. All along, I've been saying that quadratics can have up to 2 solutions. I've been trying to be careful, although I may have slipped time in and time out, but I've been trying to be careful about not claiming that every quadratic has got 2 unique solutions. All right? Does it have 2 solutions? I guess 3 and 3. But really, I think most people would say there's only one solution, x equals 3. What's my y value? Well, my y value is going to be 2 times 3 minus 4. I'm just going to use this equation to figure out what it is. That's 6 minus 4, and that's 2. So my only solution is 3, 2, and I really shouldn't write down that I've got intersections at 3, 2 and 3, 2. That would be weird. What would that even mean? It's like, yes, I have a dog, and I have a dog. It means I have a dog, right? That's it, right? There's only one point of intersection, which is a little weird if you think about it, right? There's only one point of intersection. So let's see how that plays out in part B. Let's take a look. Part B. Solve the system graphically by graphing both equations on the grid provided. The line and the parabola are known as tangent to one another because they intersect but don't cross one another. So let's see how that looks. It's kind of hard to almost imagine how a line and a parabola can intersect only once, but let's take a look. All right. So first things first, I'm going to graph the equation of the line using slope and y-intercept. All right. So first things first, I'm going to graph this thing using a slope of 2 over 1 and a y-intercept of -4. All right, so go down to -4, up 2 to the right 1. You're probably sick after all of these years of thinking about how to graph a line, but still have to do it. That was pretty good, if I do say so myself, 2x minus 4. Now the other thing we have to do is we've got to create a table of values and we've got to plot them on here, all right? Now, you've seen how to do that before, so I'm going to exit out of here and I'm going to bring this thing open. Let me actually set up a new document. Nope, I'm going to add a graph, and I'm going to put my parabola in there. Oh, why do I keep doing that? As if it's not small enough already. There we go. X squared minus 4x plus 5. All right, so x squared minus 4x plus 5. Excellent. I just need that table. There it is. All right. Now, man. If I only knew why that was happening. Technology. Okay, so I've got my table of values. I'm going to have to definitely make it small in just a moment in order to get this thing plotted on that graph grid, but I can see them, right? I'm going to plot the point -1, 10, 0, 5, 1, 2, 2, 1, etc. Okay? So I'm not going to even write down my table of values. I'm just going to go on to handheld. It is a good idea to write down your table of values. It's a little bit trickier for me up on this board, but here we go. So I've got -1, 10. I've got 0, 5, 1, 2, 2, 1, 3, 2, 4, 5, and 5, 10. All right. Let me just move this down here, move this out of the way. So now I'm going to graph my parabola. All right, not the prettiest thing, but it'll do. Label its equation, y equals x squared minus 4x plus 5. All right, and let's take a look at this, right? Remember, I found that the solution, algebraically, it was 3, 2. And that is the point right here. Right? And we call this line and this parabola tangent, right? Most of the time, right, obviously, if a line was drawn across here, let me just change my color. real quick. Most of the time, if I drew a line across a parabola, it would touch it twice, right? Something like that. But this parabola literally, this line literally goes up, touches the parabola right at that point, but sort of, if you will, stays on the outside of it, except for hitting at that one and only point, right? So it doesn't actually have to cross it to intersect it. It can come up to it, touch it, and then kind of keep moving on, all right? And this brings us to the last little piece of the lesson, letter C, all right? Let me go back to blue here. Letter C. How many different possibilities are there for the number of solutions to a linear quadratic system? Make sketches of each. Well, I'd like you to pause the video right now, and I'd like you to think to yourself, right? If I drew a parabola and I drew a line in the coordinate grid, right? How many times would they have to intersect? What are all the different cases? Pause the video now and play around with it a little bit. All right, well, the most common case was the one that we saw the first few times, which is that I'm going to have two, right? So I've got the scenario where I've got a parabola like this, and I've got a line like this, and I've got two, right? So there's two solutions, right? And then I have the one that I just saw, which is that I've got, some kind of parabola, and I've got a line that just comes up, grazes it, and then goes along on its merry way, and that's only one. But there is one other possibility, and that is the possibility, you'll explore this a lot more later on in another course and a little bit more in this course, but there is a possibility that they don't intersect at all. All right, so let's wrap it up. Now, today what we did is we looked at linear quadratic systems, and solving these was similar to solving linear systems back from Unit 5, right? We have two primary ways of doing it. We either graph the line and the parabola, and we find their intersection points graphically, either using a piece of graph paper or by using our technology. Or, more commonly, we solve them algebraically by setting the equation of the quadratic function equal to the equation of the linear function, right? When we solve them, we do normally will expect to get two values of x, which then give us two values of y, and hence two intersection points. But as we saw in that last exercise, we can actually have two intersection points, one intersection point, or none at all. Now that none at all case is going to have to wait at least until the next unit when we kind of look at why a quadratic equation might not have any real numbers as its solutions. For right now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.